So there is another method by which we make approximations, and this one involves Newton's method, which is it's fairly unique in its method or its approach to doing this. We're going to focus on a couple of these objectives. We're not going to do this last one. Determine when Newton's method does not work. We're not going to do that in this video. We're going to focus on these first two topics, and then when you get into the homework with Newton, you may find that there are a couple of problems you're unfamiliar with. There are some videos there, and you can let me know if you need some additional instruction on those. But we're going to take a look at really this screen right here. Here's what I wanted to focus on. So I'm going to zoom in on this, and well, I said I was. What I want to do is show you really what we're doing with Newton's method. Okay, so if you look right here, okay, you'll notice that we have this function. Okay, our function looks like this. So I have to talk real quiet because I have to concentrate on tracing that line. Okay, but then we have these additional lines. Okay, so we have x1 here, and then x2, all right, and x3. And so what we're doing is we're repeating a process where we're trying to find where this thing crosses the x-axis. So now that I've made a mess of that, we'll let you go in and see what we're doing. X1 is a tangent line, x2 is a tangent line, and x3 is a tangent line. And the goal is to try to figure out where this thing actually crosses the x-axis. So graphically, that's what we're doing when we're looking at Newton's method. Okay, so let's take you back here, and we'll kind of walk through just a little bit of this so you get an idea of our approach. Okay, the question in hand is trying to solve an equation that's equal to 0. Most of the time, we're working with problems that are really easy to do. Think about one like this: 3x minus 2 equals 0. Although our answer is a fraction, it's fairly easy to do. In this section, we take a look at a technique that provides an efficient way of approximating the zeros. Now again, we're approximating, so we're not finding the exact value of those things. This technique makes use of tangent line approximations, and we've already seen how those tangent line approximations work. If you consider this, if we set ax plus b equal to 0, that's a fairly easy problem to solve. And we just finished talking about 3x plus 2 equals 0. That was a fraction. This thing is easy to solve, right? We use the quadratic formula. But when we get into polynomials where we have degree 3 or higher, it gets really tricky. Take a look at this one. Okay, so this one right here, x to the 5th plus 8x to the 4th. That's a problem that not many people want to solve. Newton's method makes use of the idea of approximating solutions. Okay, so we sketch the graph and we can estimate what the root is. So a root is it's just a fancy way of saying an x-intercept. Okay, so you may say root, and I want you to think x-intercept. If this x0 is an estimate, then we can draw tangent lines to the function at x sub 0, where f prime of x of 0 is not equal to 0. In other words, it's not a horizontal tangent line. Okay? x1 is going to be the next approximation to the actual root. So basically, we start out with a guess. Okay? X of 0 is a guess, and we're going to use that guess to work our way towards the actual root. It says typically x of 1 is closer than x of 0. So x of 1 is going to be a number that's closer to our actual number, our actual root. Then we draw the tangent line. This tangent line also intersects the x-axis, producing another approximation x sub 2. So that's the idea, is that we're getting tangent lines that approach the actual x-intercept. Okay, and that's what the purpose of this picture was. So sorry, I meant to grab the eraser there. It's not. There we go. So the idea is we have a tangent line, okay, and that's going to generate an x-intercept, and we're going to use that x-intercept to draw another tangent line. So you can see my first tangent line is tangent to the curve at this x value. The second tangent line is tangent to the curve at x sub 1. And then I'm going to go tangent to the curve at x sub 2. And eventually I'm going to get a tangent line that intersects the x-axis at the same place the graph does. Okay, so we're using those tangent line approximations to determine where this graph crosses the x-axis. All right, so let's talk about how we actually go about doing this. Okay, we mentioned we're using the tangent line approximation. So this should be somewhat familiar to you, especially if you have finished the assignments from the last section. X sub 1 has to satisfy this equation. So what we have is y equals f of x sub 0 plus f prime x of 0, x minus x sub 0. That's going to give me a value. It's going to give me an x sub 1 value. Now I'm going to do x sub 1 equal to x sub 0 minus f of x sub 0 over f prime of x sub 0. And this is going to be the general equation we use when we look at using Newton's method. Then x sub 2 is going to be equal x1 minus f of x1 over f prime of x1. And take a look, x3, if we were to do x3, it would be x sub 2 minus f of x sub 2 over f prime of x sub 2. Okay, so you can see how the previous value is being used in the next value. In math, when we talk about the previous value, if our current value is n, our previous value was n minus 1. And our next value would be n plus 1. So I know there's a lot of abstract going on here, and you're probably thinking, are you ever going to work a problem out? And I am. I'm going to work one out right now. So what we want to do is take a look at how to use Newton's method. And again, this is the general form that we're going to be using as we tackle these. Use Newton's method to approximate the root of this guy. What is the equation for x sub n plus 1? So there are two questions here. There's one question here. We want to figure out what is the equation for x sub n plus 1. Well, we're going to take x sub n, and there's a typo or two here in this PowerPoint. I wanted to point this out. We're going to take x sub n, right? There's x sub n, and we're going to figure out what f of x sub n is equal to. So I'm going to replace all of these x's with f x sub n. So I'll have 2x sub n to the third minus 4x sub n squared. And this is where one of the typos is. It should be 5x little bitty n. And the same thing here. It should be 8x little bitty n. All right. This is my equation. So x sub n plus 1 is equal to, and I apologize, I'm trying to write as neatly as I can. This pen can be difficult to work with from time to time. 6x sub n squared minus 8x little bitty n plus 5. And then in the numerator we have 2x little bitty n to the third minus 4x little bitty n to the second plus 5x little bitty n minus 3. This is our equation for x sub n plus 1. Now, as you're going to see in the next couple of examples, we're going to go in and use that to estimate the actual root. So let's take a look at this one. We want to estimate the square root of 2, or approximate the square root of 2. So f of x is x squared minus 2. Okay, we're going to let f of x equal x squared minus 2, and x sub 0 is going to be 2. Now, this will be information that you're given in the problem. You're not going to have to determine what this is on your own. Again, that's something that we'll work with you on. Now, the reason where that's coming up is we have, just so you know, we have x equal to the square root of 2. If I wanted to get rid of the square, I would square both sides. If I wanted to get rid of the square root, I would square both sides. And then that's where x squared minus 2 is coming from. Okay, this is the equation that generates the square root of 2 if that equation is equal to 0. All right. So again, you probably got more than you wanted right there, but that's okay. I think it's worth, having a discussion on where that equation came from. Now again, most of the problems you're going to tackle, they're going to give you what that equation is. Okay, so with that in mind, it says we want to figure out what is an approximation for the square root of 2. And notice they choose x sub 0 to be 2. You could have chosen x sub 0 to be something something bigger than the square root of 2, but you can't choose it to be smaller than square root of 2. So that's why 1 would not work right here. Now notice what we do. We have x sub n equal to x of n minus 1 minus f of x of n minus 1, f prime of x of n minus 1. Okay, so we have the current term equal to the previous term, right? That's what that is. Now there is some math that's going on right here that I wanted to explain to you. I felt like it may be a little bit hard to figure out what's going on. So we have x sub n minus 1 minus x squared n minus 1 over 2x n minus 1, okay? This is like saying x squared over 2x, okay? So basically what happens is we have this x sub n minus 1 minus, okay, if I had this, those x's would cancel and I'd be left with an x up top. So basically I have 1/2 x sub n minus 1. And then I'm going to break up the second part to be minus 2 over 2x sub n minus 1. Basically, I broke this fraction up into two different pieces. There's a negative out front, so I need to make this a positive. Okay, I'm distributing that positive. Or I'm distributing the negative that generates the positive. So the 2's cancel, and we have 1 over x sub n minus 1. Again, if you're wondering where all this is coming from, right, we're treating these x sub n minus 1s kind of like they're x's and canceling out the like terms. This is 1 minus 1/2. Okay, 1 minus 1/2 is just 1/2 x sub n minus 1 plus 1 over x sub n minus 1. Let's see here. Yeah, 1. Okay, so what happened here, to go from here to here, Newton is getting, the creator of the PowerPoint is getting a common denominator. Notice that this is like x over 2. So this thing right here is like saying x n minus 1 over 2 plus 1 over x n minus 1. So I would need an x sub n minus 1 here. And I would need a 2 here and here. All right. So I'm not really keen on what's happened here, but if you again, if you have questions, you can reach out there. I'll be glad to help you. So, excuse me, had a momentary lapse there. So what we're doing is we're factoring out a 1/2. We'll bring the 1/2 out front. And by bringing the 1/2 out front, I put a 2 here. Notice if I do this times this, the 2's cancel, right? This 2 cancels. So I would get 1/2 x sub n minus 1 plus 1 over x sub n minus 1. So again, they're factoring out a 1/2 here, and it turns that numerator to 2. So you can disregard what I said about a common denominator. That is not what they were doing. They were factoring out a 1/2. Okay, so what we're going to do is we're going to say if x sub 0 is 2, okay, x sub 0 is 2, and we know that x sub 0 is 2 because we said that right up here, x sub 0 is 2. X sub 1 is going to be, now notice this is x sub 1. X sub 1 takes into account the previous term. So x sub 1 would equal the previous term right there. As our n minus 1. All right, so 1/2 x sub 0 plus 2 over x sub 0. And again, we're getting those because if we look at x sub 1, then x sub 0 is the x sub n minus 1, right? 1 minus 1 is 0. Notice that we plug in 2 for those x sub 0s. 2 over 2 is 1. 1 plus 2 is 3. And this would turn into 3 over 2 or 1.5. So for the next approximation, we're plugging in 1.5 in for x. Okay, so this is x sub 2. We use x sub 1 in our next approximation. And you may need a calculator to do this, just so that you're not struggling too bad. But what I would probably do is 2 over 3/2. and that would give me 4/3. So you can choose to use a calculator here to figure that out, which is probably what I would encourage. And you'll get 1.4166667. We're going to use that value in our next one. So our next one, our x of 3, would look like this. 1/2 times 1.41416 repeating, right? Plus 2 over 1.416 repeating. And we would simplify this to get that next value, that x of 3. And then I'm going to use that one in x of 4, and I'll use that one in x of 5. So you can see how closely we get down here with x of 5 to the actual square root of 2 value. Notice in this one, we only want to be able to write an equation for identifying what this is going to equal. Okay, so it says, what is the equation for x of n plus 1? So using our Newton's method, x of n plus 1 equals the previous term. Okay, so if we're looking at x of n plus 1, the previous term was x of n minus x of n squared minus 35. So again, we're trying to figure out, well, where does 35 come from? We're plugging the square root of 35 in right here. Okay, so this f of x is that equation they gave me, x squared minus 35, and then the derivative. So let's talk about the derivative right here, f prime of x of n. So the derivative of x squared minus 35 is just 2x. So here is that equation that I was looking for. This one's very similar. So we do the same thing. F of x of n is just going to be x of n squared minus 71. That's what we have in place of f of x. And then on the bottom we have the derivative of x squared, which is 2x. And so there's my equation for finding that, or approximating the square root of 71. Yeah, some of these are a little more, in your face, a little more challenging than others. Let me know how things are going. I'll be glad to give you those supplemental videos if you need. And again, you can find additional resources inside Newton.